Yeah, now we are going to start with a topic that is the buffer solution, right? Now you are familiar with the acid, you are familiar with the base, and even you are familiar with the neutral nature of the solutions, right? So now we are going to start with the buffer solution. So what is the buffer solution actually? So I'm just stating an example for you so that you can remember this buffer solution in a proper manner, right? So have you ever seen water? Yes, you have, right? So what is the chemical nature of the water? Is it acidic? Is it basic, or is it neutral? We know that pure water is always neutral, right? So you're right, in that case the pure water is always neutral, right? So suppose I have a beaker and I have the pure water in it, that means it is neutral, right? Now what I'm doing is I'm adding a few drops of acid to it. Right, I'm just giving you the pure water and you are adding few drops of acid to it. Then what will happen? Will it remain neutral? No, it will not remain neutral, as its pH will decrease and it will become now acidic in nature because you have added few drops of acid to it, right? Similarly, if I give you the pure water which is neutral, and you add few drops of base to it, then what happens? Is it going to remain neutral? No, it is not going to remain neutral because it will become alkaline now, right? So that means, like we took a water, earlier it was neutral, but when you add acid to it, it becomes acidic, and when you add few drops of base to it, right, it becomes somehow alkaline. So that means the pH is just altered, right? That means earlier it was 7, that is, it was neutral. When you add the acid to it, it just decreased, right? And when you add base to it, what happened? It just increased. That means it no longer remained neutral, right? But we are in urgent need of the solution whose pH does not, you can say, alter on adding a few drops or substance into that, right? That means, again I'm repeating, we are in urgent need of the solutions. We need a type of solutions whose pH approximately remain constant when you add some acid or base to it, right? That is called as the buffer solution, right? So what is buffer solution? Buffer solution means a solution which can resist the change in pH, right? That means when you add acid or base to it, then it has a tendency, it has a powerful action, it has the ability that it can resist the change in its pH, right? So this is called as the buffer solution, right? So I'm just stating an example for you that if I ask you that, have you ever come across the buffer solutions? You might have, but you don't know actually what is the special property it possesses. That is why you're not aware that yes, this common substance which you know is a buffer solution, that is the blood. You know, the blood contained in a body, you know that we take an acidic food, we take an alkaline food, but still the pH of the blood remains the same. That means the blood has the ability to resist the change in pH when you take an acid or when you take an alkaline or a base, right, into your body. So that means it has a tendency to resist its pH because its pH approximately remain constant. So that means blood is also a buffer solution, right? So this is a buffer solution, right? I think you are clear with the definition. Again I am repeating, buffer solution is that solution which actually has a special ability. That means it can resist the change in its pH, or you can say the pH remain approximately constant when you add acid or base to it, right? So this is called as buffer solution. Now the question must be striking in your mind that what special thing it has that it can resist its pH, right? As the water cannot. If we add acid to water, its pH gets changed, right? If you add base to it, its pH obviously gets changed. So what is the special property which the water doesn't have, which is our universal solvent, and many other solution like the blood I'm talking about, they have, right? So what is that? We are going to take up in detail now, right? So actually these buffer solutions contain weak acid or weak base in them, right, which is responsible for the buffer action. That means their ability to resist change in themselves, right? So let us just see that how these weak acid and weak base just help the buffer solution to resist its pH when some few drops of acid or base is added to it, right? So before we do that, I want to tell you that buffer solution is of two types. Please write in your copies that buffer solution is of two types, that is, it is the acidic buffer and it is the basic buffer. So we have two kind of buffer solution. One is acidic buffer and the other is basic buffer, right? So that means this acidic buffer, what does this acidic buffer contain? This contains the weak acid, plus it also contains the salt, which is formed of weak acid plus strong base. Right, so that means acidic buffer is that which contains the weak acid. As I told you, they have the weak acid, right? So they have the weak acid plus along with the weak acid they have the salt, and that salt is formed of this same weak acid combined with some strong base, right? I'll be explaining you with an example further, but for this moment I just want you to know that what does they contain, right? And when we talk about the basic buffer, it contains the weak base plus it contains the salt, which is formed of again the same weak base plus strong acid, right? So now I'll just explain you that how they actually works. So I'm just taking into consideration one by one. So I'm just starting with the acidic buffer first to explain you how the buffer action is performed, right? I'll just divide the board into two so that it is convenient for you to see. So we are just studying about the buffer action. What is the buffer action? Ability to resist the pH. That is the buffer action, right? We know that buffer solution is that which resists the pH. So that means their ability is called as the buffer action. So that means buffer action is the ability of buffer solution to resist the pH, right? So I am taking into consideration the acidic buffer first. As I told you that acidic buffer actually consists of, as I told you, weak acid plus salt of weak acid and strong base. Same I am taking here. So that means it consists of weak acid plus it consists of salt, which is formed of weak acid and strong base. So let us take some example to explain in a proper manner. So the weak acid, what I am taking an example is acetic acid, and plus I am taking a salt which is formed by the combination of weak acid, again the same one, acetic acid, and the strong base, let us take the sodium hydroxide. So they will result in the formation of salt, that is sodium acetate, right? So that means we know that the acidic buffer contained the weak acid and the salt of weak acid and strong base. So this weak acid I have taken acetic acid, and the salt I have taken is by the combination of acetic acid, that is the weak acid, with the strong base, that is NaOH, which both combines to give this sodium acetate, right? So what we are going to see in this case, acidic buffer, what we'll observe that this solution contains, because we know it is a weak acid, it will be in ionic equilibrium with its acetate ions. That means partially dissociated, right? That means few molecules undissociated and few ions of acetate and hydrogen, right? It is already there in the solution, right? And what happens to this? As we know, salt are a strong electrolyte, so they completely get dissociates. So that means in the solution these things are already present. That means we have the acetate ions, we have the hydrogen ions, and we have the undissociated this acetic acid. Equilibrium sign is because it is a weak acid, it partially dissociates. They have the tendency to give this, and even they have the tendency to reunite and give this acetic acid back, right? And similarly the sodium acetate, it is a salt, we know it is a strong electrolyte, it completely dissociates, so it dissociates to form acetate ion and sodium ion. So these things are already present in the acidic buffer, right? Now we are going to see that how it resists the pH. So what happens? First I am adding an acid to it, right? Suppose a few drops of acid. For example, I take an acid as example HCl, right? That means I am adding HCl to this solution which already contained this, right? This solution already contained these things, and what I am doing is from externally we are adding an acid to it. Acid, for example, I am taking the HCl, right? So that means this acid will be giving, it will be giving hydrogen ion, right? Then what this hydrogen ion will do? It will just increase the hydrogen ion concentration and it will affect the pH. This is what we expect, right? This is what we expect, that when we add acid, it will dissociate to form hydrogen ions, and these hydrogen ions will increase the pH. That means it will, you can say they will just make the solution acidic now, right? But actually this doesn't happen. This hydrogen ion do not affect the pH. It do not affect. I wrote affect because it was supposed to affect, but it is not affecting. That is the, you can say the buffer action, where the buffer is playing a tricky task to resist the pH. pH. So just look at the board that how it is just playing that tricky task, right? So this acid did dissociate to form hydrogen ions. These hydrogen ions were supposed to alter the pH, but actually they are not altering. Why they are all not altering, and where these hydrogen ions are going? The question is that now, right? So where these hydrogen ions are going? These hydrogen ions are taken up by the acetate ions, that is from these. From where do we get this acetate ions? Obviously we get from these undissociated ones. And what they are doing, they are just combining to form acetic acid, right? So that means these hydrogens are utilized now. We are not left with any kind of hydrogen ions present in the solution that can alter the pH, because they are getting consumed by the acetate ions, right? Similarly, what happens? I'm repeating it again. So we add acid to it. Acid is giving hydrogen ion, which is obviously going to affect the pH, but it is not altering because it is getting consumed, right? So who is consuming this hydrogen ion? Obviously who is consuming? It is the acetate ion, but this acetate ion is not coming from this acetic acid, it is coming from this salt, right? So it is coming from this sodium acetate ion, these ions, right? So these are just neutralizing these hydrogen ions. So these are coming from this sodium acetate salt. There is no need to write it, but you should know that which acetate ions are just combining with the hydrogen ions. So these are the acetate ions of the sodium acetate, right? So they are just combining to form the undissociated acetic acid. So this is how when we add acid, the pH doesn't get altered, right? Now let us add base to it. So base, suppose I am adding NaOH, right? So obviously it is going to, it will dissociate and it will release these hydroxide ion, right? Now that means these hydroxide ion can alter the pH and can, or you can say, affect the nature of the solution, or it will make the solution alkaline. What is it? It is supposed to do, right? But actually it is not, you can say, affecting it, because they are also again getting consumed. Now the question comes, who is going to consume these hydroxide ions? It will be consumed by these hydrogen ions, right? So that means these hydrogen ions will combine with these hydroxide ions from base, and they will form water. So again these hydroxide ions are consumed. So we are not left with any kind of hydroxide ion which can alter the pH. So this is how they are showing the buffer action. That means they have certain reserved things which are just combining them, and they are not letting allowed to disturb the equilibrium or to alter the pH, right? So similarly, what happens when we dilute the solution? Dilute the solution, we are adding water to it. We know when we add water, water will obviously dissociate to give H ions and hydroxide. This is what we are going to get if we'll add water, right? So what happens when we add water to it? These hydrogen ions are consumed by the acetate ion of the acid, these ones, and even they will get consumed to form undissociated this. So this is how the pH doesn't get altered, right? I think it's clear. Again, I'm repeating, we have the acidic buffer in it, this is present and even this is present, right? So when we add acid, acid gives rise to hydrogen ions. So this hydrogen ion can alter the pH, but actually it is not altering because it is getting consumed by the acetate ion of this salt, right? So that means they are gone. So they will not alter the pH, right? Because we are not left with the extra hydrogen ions who can alter the pH, right? The second thing what we are doing, we are adding base to it just to check that when we add base, so pH get altered or not, right? So we are adding base, it will give rise to hydroxide ion, and obviously it is also, it seems that it will also alter the pH, but it is again not altering the pH because it is getting consumed by the hydrogen ions of the acetic acid, right? So again these are consumed, we are not left with any kind of hydroxide ion which can alter the pH. So again the solution can resist the pH. Similarly, we are adding water to it, so we get the hydrogen ion and the hydroxide ion. So similarly, they are just combining. So with the hydrogen ions, what is combining? It is combining the acetate ions of the acid. In this case, the acetate ions is from salt, right? But in this case, the acetate ion is from the acid. This you have to keep in mind because it is little bit confusing, right? So when the acid hydrogen ion is to be neutralized, we have to take into consideration acetate ion produced from the salt, and when we are taking into the consideration on adding the water, these hydrogen ions are consumed by the acetate ions of the weak acid, right? So in both ways, what we get to see that these acetate ions are just getting getting consumed, and they are just forming again the acetic acid, undissociated one. So that means, according to Lee-Chartley principle, which side will be favored? Yes, you are right. The more dissociation will be favored because acetate ions are actually getting consumed with time, right? So this is how they are able to, you can say, resist the change in the pH when some acid, base or water is added to it, right? So now what I want to explain you next is that what affects the pH now. What affects the pH? Like for the acidic buffer, what is the, you can say, the effect on the pH? So I am just going to show you the pH of the buffer solution, that is the acidic buffer. Right. So what we are going to do in it, the next is, as we know, this acidic buffer contains the weak acid. Suppose I am taking HA, we add water, they form hydronium ion, plus they form A negative. You know that, right? And similarly, we have a salt also, of weak acid and strong base. It will completely dissociate. We know it is a strong electrolyte. It will form this, right? So for this, I can write the equilibrium constant expression, that is, or you can say the ionization constant for an acid expression. It comes out to be H3O positive concentration of this, A negative concentration divided by concentration of the reactants. This is what we have, right? Because where this H2 has gone, you know that we write the expression for the equilibrium constant, then we multiply this H2O with the K and we get the Ka, right? That is the ionization constant for an acid, right? So this is the expression. Now, if I want to know the concentration of the hydronium ion, because we know that pH is somehow equal to minus log hydronium ion concentration, right? So that means to calculate the pH, we have to know the concentration of the hydronium ion. So this is what I am doing here. I am just keeping it here and just shuffling everything. So I have this. Right. Now, what is the concentration of this A negative? This is here. That means this A negative will be just equal to the concentration of the salt, because this will be formed as much, or you can say at equilibrium we have that the concentration of this and this are just equal, right? So we can just replace it by Ba. So that is what I am doing. Concentration of hydronium ion is equal to Ka HA divided by Ba. Now the question comes, what is the HA and Ba? You know that. So I can write the expression this as, we know HA is acid, right, and Ba is salt. So we have this. Now I am just putting this value into the pH expression. So we know pH is equal to minus log hydronium ion concentration. So I am putting this value of hydronium ion concentration here. So what do I get? pH is equal to minus log Ka acid upon salt, right? I can write it in a different manner also, where pH is equal to minus log Ka minus log concentration of acid to concentration of salt. Yes, we can do that. You know how to write these kind of expressions. We did in pH. So again, we can write as pH is equal to we can write it as this also, just shuffling them. We have pH is equal to pKa plus log concentration of salt to concentration of acid. So this is the, you can say, the pH of the acidic buffer. I think it's correct, or you know that how to do it. First just write the expression, then write the acid, you can say the expression for the constant, equilibrium constant, get salt dissociated, write the value of Ka, find out the value for H3O hydronium ion, put it in the pH is equal to minus log hydronium ion concentration, right, like this, and just go on solving and you will get this kind of value. So this is what actually the acidic buffer is. So I think you are clear that what is the buffer solution, you are clear what is the acidic buffer, you are clear how can you find the pH for an acidic buffer, right. So in the similar manner we are going to do again now for the basic buffer.